Hello. Hello. Can you hear me? Uh, Hello. Hello. Can you hear me? Is my voice clear? Saksham, can you hear me? Saksham, can you hear me? Okay.
Aryan, your voice is not clear.
Saksham, do you know about today's topic? Hello, Saksham, are you here? Uh, Hello, Saksham, are you here? Your voice isn't clear. Is it clear now?
Yes, Aryan.
Saksham, is it clear now? The voice?
Yes, Aryan. Your voice is now clear.
Okay. So, Saksham, today our topic is about uh, elements formation. So we will be talking about how elements are formed, and we'll firstly go on about how the elements, like uh, the things that make elements up, were discovered, and their role in it, and how are they useful to us. Okay. Should we start?
Yes, Aryan. Aryan, you can wait for some time if someone comes.
uh, can you repeat yourself, Section?
Aryan, you can wait for some time if someone comes.
Okay. So do you know about today's topic?
Yes, Aryan. You might be going to discuss about the periodic table.
Okay, no, we are not going to discuss about the periodic table, but we are going to talk about the elements in it, about how they are formed, and what processes do they follow to make that happen. So, do you know about these decays?
Yes, Aryan, I know about beta decay and alpha decay, but can you explain to me in brief, like what is there in short?
Okay. In short, we will be talking about how the elements were discovered, like the atomic part, subatomic particles were discovered, and their role in these decays. We will talk about the different types of decays and RNS processes about and how heavier elements are formed.
Okay, Aryan.
Okay. Uh, Alan has joined, so Alan and Mrityunjay Bhaiya has joined. So, Mrityunjay Bhaiya, do you know about this topic?
Hello, Aryan, good afternoon. Yeah, I am here to hear what you can say. You need to educate me on this.
So today, in this topic, we are just going to talk about these decays, and firstly, we will just talk about how the uh, particles like neutrons and protons were discovered, and then we'll move on to these decays and RNS processes about how they form heavier elements. So this is all the things that we will cover this in this presentation. So so I think so we should start by now. So uh, for those who don't know me, I am Aryan and I was born in Bihar. I am living in Ludhiana for my education purpose. I am 13 years old, and for today, our topic is about element formation in the ancient philosophy. So, the ancient Greek philosophers proposed that matter cannot be infinitely divided. He argued that slicing substances eventually hits an uncuttable, indivisible limit. So, the solid cube symbolizes this ultimate unbreakable particle, the atomos. This revolutionary theory challenged the popular belief that atoms were continuous, that matter was continuous, laying the foundation for modern physics. So his name is Democritus, something like that. So he's an ancient Greek philosopher, and he stated that matter cannot be infinitely divided. So this is where our journey begins. So this is John Dalton, and in 1803, John Dalton transformed ancient philosophy into modern science. He proposed that elements consists of unique, indivisible solid atoms resembling billiard balls. Dalton's sketchbook circles show that chemical reaction do not uh, destroy matter; they simply rearrange these permanent spheres into new combinations, establishing quantitative chemistry. So, in 1803, John Dalton he proposed uh, that uh, there were solid atoms and they did not and they weren't like he said that this is the place that this is the limit that after that it cannot be broken down further. But what happened after that is that we discovered the protons, the neutrons, and the electrons. So there were many great changes to the John Dalton atomic structure that we'll just discuss in this presentation. So J.J. Thomson and he shattered Dalton's solid atoms by discovering the electron. By firing a glowing green ray through a vacuum, he observed that the beam bent towards a positive magnet. This proved that the ray was made up of lightweight negative particles originating from inside the atoms, revealing the first subatomic particle. So he discovered the electrons. So what happens is that he took he took something in a glass tube and then he brought an magnet very close to it, and he had coated I think so zinc sulfide or something fluorescent around the tubes. And what happened when that magnet was brought near uh, the fluorescent lights, he saw the light bend, the beams bend. And after what you can say, there is a system I think so. It was used in the early times of science. It was used to find the properties of these things by their curve. And as we know that if it was lighter, it would give a bigger curve, and if it's heavier, it wouldn't bulge, it wouldn't move that much. So he discovered that these are very light, and these had negative particles because they were getting attracted to the positive, the magnet. So so this is how the electrons were discovered, and the plum pudding model. And so J.J. Thomson visualized the atom as sphere of uniform positive charge embedded with tiny charged electrons. He compared this structure to a popular dessert. The positive paste was the pudding, and the electrons were the scattered plums. This model maintained overall electrical neutrality while incorporating subatomic particles. So at a party, what happened that J.J. Thomson saw saw a cake, and then his that and model came to his mind, and which we now known as the plum pudding model, where the positively charged is spread, and the electrons are like plums in the atom. So this is the plum pudding model. So ladies and gentlemen, do we have any questions? Saksham, do you have any questions? Hello, Saksham, are you here?
No question to check. You can continue.
Okay. Henry Becquerel. Okay, I think so. Okay, Henry Becquerel. So in 1896, Henry Becquerel accidentally discovered radioactivity in a dark Paris drawer, intending to use sunlight to make uranium glow on photographic plates. Bad weather forced him to lock the materials away. Days later, he developed the unexposed plates and found the perfect dark silhouette of the uranium salts, proving that the element continuously, spontaneously emitted a powerful hidden energy without any light source. So back in the day, what happened is that there used to be a camera film which people used to like take pictures with, and what he intended to do was to make the uranium elements glow in the sun. But due to very bad weather in Paris, what happened? He locked them away in a dark drawer, and after some time, when he opened that, he observed that he observed the glowing radioactive uranium salt. So that is how uh, radioactivity was discovered accidentally. So Marie Curie. So Marie Curie and Pierre Curie worked in a leaky, freezing shed, manually stirring boiling vats of toxic pitch blende ore. She made a groundbreaking realization that radioactivity did not depend on how chemical was shaped or mixed, it came entirely from the atoms itself. Through this exhausting work, she also discovered two brand new highly radioactive materials, polonium and radium. And how did she know that it came from the uh, atoms, the atomic structure? Because no matter what she did, like uh, grind them, mix them with other elements. the radioactivity was still there, and because of that she came to the conclusion that it was coming from the atoms itself. The atoms of radium and polonium, the light was coming, that energy from was coming from them. But people at that time did not realize how it was coming, and uh, she also discovered two new radioactive elements, polonium and radium. Ernest Rutherford. So, Ernest Rutherford tested Thomson's Lamponi model by firing heavy positive alpha particles at an incredibly thin sheet of gold foil. He expected the particles to fly straight through the soft atoms. Instead, uh, while most passed through unaffected, a tiny fraction bounced very violently. These shocking results prove that atoms' mass is concentrated in a tiny, dense positive center, now known as the nucleus. Uh, so, these alpha particle beams were like in a Plumpton model, they should have just flown through them. But what happened in this case was uh, uh, most of them passed through the gaps of the atoms, and some of them reflected back very violently. This meant that the mass was concentrated in a very very small place. And while doing his calculations, he found that it's about 100,000 times more smaller than an atom. So, and these alpha particle beams he had discovered some years earlier, and the gold foil was about 20 to 25 atoms thick. So, uh, this is how he proved the plum pudding model wrong by firing alpha particles at the gold foil, now known as the gold foil experiment. So, Saksham, uh, are there any questions by anyone? Okay, I don't think so. Okay. So, by smashing. Okay, so now we are going to the discovery of protons, and by smashing alpha particles into nitrogen gas, Rutherford no now produce a particle stream of lightweight positive particles. He realized these were actually a hydrogen nuclei. He named this fundamental building block the proton, proving that all heavier elements are built from combinations of these positive carrier packed tightly inside the nucleus. So what happened is that uh, he shot alpha particles at at nitrogen, which is an noble gas, and he took the measurements. He took it in a glass tube, and he knew that the particles only had 7 centimeters or 8 centimeters worth of energy to like uh, they had this energy to cover uh, this much distance. But what he observed that they were going much farther away. Like he also had a paraffin bags, paraffin some material like that, and they were so heavy that they knocked out these the protons out of them. So here he knew that if it had been something else, it wouldn't have done that. Because first of all, the people thought that it was just gamma ray or something like that. But he knew that heavier, like light is light, it can't push something like that. So what he then thought was that if it was light, that particles, the parallax had not been the protons would not have been knocked out of that, right? Instead, he then noticed that these were like not into going into the electromagnetic uh, counters, and so he then realized that this is a neutral particle. So this is as heavy as the and he also came to the conclusion that they were as heavy as the neutrons and protons. The weight difference. Uh, Rutherford proton discovery left a massive mystery. The nucleus was far too heavy. When scientists weighed a helium nucleus, it carried as much as four protons, but it only carried two positive charges. The scale tilted heavily, proving that a hidden, uncharged particle with equal mass had to be hiding in the core. So this is where neutrons come in. So James Chadwick solved the missing mass puzzle by bombarding beryllium with radiation. This released a highly penetrating stream of uncharged particles. Because these carry no political charge, they easily pass through fields that block protons, and he proved that these neutral anchors matched protons' weight exactly, completing the nucleus. The modern atomic structure. So the classical model of the atom is officially complete. The negatively charged electrons orbit dynamically inside a clearly fixed, defined paths, resembling a miniature solar system. At the absolute center sits the maximum, the dense, heavy nucleus, uh, and which is tightly packed cluster of positive and neutral neutrons, and that anchors the entire structure in place. So, like this is uh, not the true model. They are not orbiting like that. In quantum mechanics, there is an electron cloud, so that is how they uh, uh, revolve around the nucleus, but not in this position. So stability, so the ratio of protons to neutron dictates whether an atomic nucleus holds together or it rips itself apart. For light elements, stable nucleus requires an equal 1:1 ratio. As atoms grow heavier, the positive protons violently push against each other, requiring excess of neutral neutrons up to an 1.5:1 ratio to act as a nuclear glue and maintain structural balance. So there's one more thing that I didn't mention is that particles like the neutrons and the protons are bounded together by a strong nuclear force. Like they have uh, what do you say that they have quarks in them, right? And these quarks are held together by gluons. So the strong nuclear force helps the atom to be stable. Okay, so alpha decay. Now we are moving to the decays. So before we move on, are there any questions by anyone? Saksham, do you have any questions?
No, Aryan.
Okay. So alpha decay happens when an oversized atomic nucleus grows too large for the short-range nuclear force to hold it together. Overpowered by the electromagnetic repulsion, pushing its protons away, the unstable core forcefully rejects a tightly bound packet of two protons and two neutrons, shedding mass to restore structural balance. Okay, so what happens is that when the atom grows way too large, what happens is that a strong nuclear force isn't enough, and the alpha decay particle after this, what happens is that it breaks, it gives an alpha particle, helium, the helium one that you see with two protons and to neutrons to make itself more stable. As you can see in the picture, the uranium decays into thorium. So its mass is reduced by 4 because it released 4 particles. What triggers the alpha decay process? When the atom gets too large, and like when it's like in the case of uranium, we saw that. And how would that particle know when to decay? So there are many equations for that. It gives us the probability, not like the exact time when it will decay. So uh, so that is but yes, they are called isotopes of that material. An isotope, like how would it? An isotope, like a heavier element. If I have uranium, and if I just take out 2 protons from it, it would become thorium. But if I add some neutrons into it, by adding a neutron to the uranium atom, we get an isotope. So there are, I think so, uh, isotopes. I think so. It's 238 uranium, like which has 4 extra. Uh, I mean 3 extra neutrons. So those are isotopes of of a substance. Yes, there are stable uranium, but there are isotopes of them. So, do you have any other questions? Okay. So so after this alpha decay, what happens is that to get rid of the extra energy, it also emits some photons. So beta decay, it alters an atom's identity without losing mass. Inside an unstable nucleus, and neutron suddenly transforms into positive proton, firing away a high-speed electron beta particle. Because the total number of nuclear particles remain identical, the atomic mass stays constant, but the brand new proton advances the element to one upon the periodic table. So, as you can see in the case of cesium, uh, it has 137 particles and is 55 on the atomic in the periodic table. But what happens is that whenever a neutron inside an unstable nucleus, uh, a neutron, like because it gets heavier, that why it becomes a positive proton. Like uh, in that case, in common sense, what people I will think is that because of a proton, if proton comes into an atom, an excess proton, it will go decay. It will decay. But the thing is, it also needs to be in check with the mass and other things. So it has to get a good balance of that. So what happens is that a neutron transforms into a positive proton, and then a neutron is a little heavier than the positive proton. So what happens? It decays an electron and a neutrino, which carries away the extra momentum and the energy, and the charge is now gone with the electron. So so in the neutron, what's happening is that there are 2 down quarks and 1 up quark. One up quark is about 2 by 3, positive 2 by 3, and 2 down quarks. Like one down quark is 1 by 3, negative 1 by 3, and by adding another up quark, what happens is that the balance shifts and it becomes one. because uh, plus plus 2 by 3 plus 2 by 3 minus 1 by 3 would always be 1, isn't it? So that is how it's becoming in positive proton. And because a down quark is heavier than an up quark, it releases those particles. So are there any questions by anyone on this topic, beta decay? Okay, what happens to the ejected? Okay, Saksham, what's your question?
My question is that you're telling that the neutron will be ejected, so why will it be ejected?
Can you repeat?
You're saying that that electron will be ejected, so why?
Okay, why is that? Like in that, when the neutron, what's happening is that there are three quarks. One is the up quark, and one is the down quark, and there are one up quark and there are two down quarks, and the proton has plus one charge, isn't it? So it has two up quarks and one down quark, and uh, in that neutron, the up quark is plus 2 by 3, and the down quark, there are two down quarks, so it's minus 2 by 3. And to get rid of that minus 2 by 3 to minus 1 by 3, they release an electron. So to carry away the charge, negative charge of that. Like if I do minus 1 by 3 by minus 1, that's how I'll get plus positive 2 by 3, isn't it? Did you get me?
Yes, sir.
Okay.
Yes, sir.
So do you have any other questions?
Yeah,
No,
Aryan.
Yes.
So can you just tell me where do you observe beta decay in real life?
In real life, this is the thing we are going to do is that uh, this is called beta plus decay. This happens in R and S processes, which form heavier elements.
Okay, but then where do you observe it?
We observe it we observe it everywhere. In the S process, the slow neutron capture, what happens is that uh, the atoms get neutrons at a very slow pace, and in our process, what happens in the supernovas, kilonovas, uh, things like that. It
when
Yes,
when the core of the star captures neutron unusually fast, forming a neutron star, there the R process happens.
yes. So when the atom gets a lot of neutrons very fast, that's called our process, and it happens in explosive events like kilonova and supernovas. So this is how we have heavy elements like silver, gold, platinum, etc.
But in beta decay, where we will observe in real life, like in real life, where just the beta decay happens, where we can observe it.
We are observing that uh, I don't like we are observing it everywhere. I think so. It also happens in our body. I think so. Uh, the
No,
age.
no. See, his question was, how can we observe it in real life where it is happening? So my answer to it will be that, see, you cannot observe beta decay in your
Yes.
in a naked eye or in your real life.
Yes, because beta decay is, you can say, similar to atoms in size and we can't observe it, but through microscopes, where
No, we cannot do that. Basically, it requires extremely high temperatures, so you cannot even observe it from a microscope. And you cannot see an atom by a microscope, so you cannot observe a microscope.
Okay.
it is basically a calculation of particle physics, where do all sorts of calculations, and they come out with these processes, and then they theorize, they simulate, they model somewhere in the from the formulas, and then they predict that okay, this might be happening there in the supernovas, this might be happening in kilonovas. So they don't observe directly, they just theorize and then formulate and then experiment.
Okay, so uh, there's a question for this. There's someone has a question is that can a proton eject a positron to become a neutron? I think so. Yes, I've also read about uh, it. This can happen. I think. So. Okay, Sakshin, you raised your hand.
Aryan, I have a question that does neutrons can play roles in these decays? Like, can they affect these decays?
Uh, can you repeat?
My question was, can neutrons could affect these decays?
Neutrons,
Deuterons.
deuterons. Do you mean deuterium?
No, it is deuterons.
Wait, I think so. It's deuterium atom only. Deuteron.
Yes, Aryan, it's deuterium.
Okay, so what were you saying about that?
Um, my question was, can these atoms could affect these decays?
Can these atoms be
Affect these decays?
affect how? What do you mean by affect decay? Uh, are you telling that they go under uh, that they go under beta decay, or you are trying to say something else? I did not get your
I
question.
am typing, you can wait.
Okay, okay, okay. So I think so. There was another question by him. So what happens to the ejected electron? So uh, so it escapes the atom entirely, and uh, and then it gets closed down by other interactions, and it may eventually get captured by another atom to become a standard electron of an atom. So because it has a lot of kinetic energy, the pull of the nucleus, uh, like the negative pull of the nucleus or the barrier of that electron atom, uh, own electron clouds would not trap it, so it flies out of that uh, atom only. So as this, and so it just gets out of that atom entirely. I still did not get that question. How can these neutrons could affect these decays? Uh,
Aryan, you do not get means. I was asking that suppose there is a deuterium atom, though, then how will it affect it? Can it affect their masses or something else? Like their
like, are you saying that what happens to the deuterium after M decay?
yes, and does it will affect that decay?
Affecting that decay, I did not get that part. You should say, like, if you're trying to say that after the decay, what happens to it? That will work.
Yes, Aryan. Yes,
Okay,
Aryan.
okay. The thing is that deuterium atom stable or not? That will matter. Uh, 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 did I answer the question? Are you satisfied?
Aryan, you did. I think you did not understand my question. Like, suppose there is a deuterium atom, and if it got close to that decays, then will its pull, like you say, if it collided, or will its and or will its pull will affect that decay?
Okay, like beta decay happens in that atom entirely, and if something like the electron comes out of that process. Okay, Alan wants to answer questions, so I think so he should. I don't think so. I understood your question very well. So what I understood is that if an atom decays very near to that, what happens is that the materials from that decay may get into that like the byproducts, electrons, so it may absorb that. Okay, I think. Okay, so okay, you meant that what if would happen if it was directed to a heavy atom? So, so uh, I think so. In my previous laboratory, uh, I so so when this the uranium has its okay. So you were talking about that. I did not get that question. So I think so. We should move to the topic now. Beta plus decay. So, beta plus decay occurs when an unstable nucleus contains too many protons, and to achieve stability, a proton transforms into a neutron. An up quark flips into heavier down quark by absorbing energy, and a positively charged electron, positron, along with a neutrino are forcefully ejected, shifting the element backward one slot on the periodic table. So beta plus decay in this what happens that the proton transforms into a neutron, and a proton is made up of two up quarks. So it transforms the one up quark to down quark plus 2/3 to -1/3, and uh, to get that it needs an electron, and then positively. Okay. So this is what happens in beta plus decay. So let's get to the element formation. So elements are formed through star nuclear processes inside stars. So the R processes and S processes are two primary neutron capture processes. So these processes explain the creation of many heavy elements beyond iron. Overview of stellar nucleosynthesis. So it occurs in different types of stars. Elements up to iron are mostly found in the cores of stars. Heavier elements are produced during explosive or slow neutron capture events. So what is our process? The R process, the rapid neutron capture, is a cosmic reaction that creates half of the universe's heavier elements than iron, like gold, uranium, plutonium, etc. So, occurring during violent neutron star emerges, atomic nuclei rapidly absorb a load of uh, free neutrons before decaying via beta minus decay into stable heavy element structures. So, a lot of new people have also joined. So, Victor has also joined, and Adriana. So thank you for joining us. Today we are talking about element. element formation, we first talk about the types of decays, about elements, about subatomic particles, how they discover, and the R and S processes which create heavy elements. So, are there any questions by anyone?
But Aryan, as you are saying that our process occurs during the neutron star mergers like supernovas, but they can also occur in supernovas. So,
Yes,
uh,
yes, they just need a place where they can absorb a lot of neutrons. So, any event that creates such circumstances would be a place ideal for our process.
that I understand, but you are saying that occurring during boiling neutron star mergers, but these are processes can also occur in supernovas, like when a star twice as massive as sun goes into supernova, then our process can also happen.
Yes, that's what I said. Is that whenever it gets a load of free neutrons, that place would be suitable for our process. I just included neutron star mergers only. Uh, there are many other places that our process can occur. What is the S process? So the S process stands for slow neutron capture process. So it occurs relatively lower in lower neutron environments, typically in giant brown stars. It produces stable isotopes along the value of stability. So Saksham, you have raised your hand.
Aryan, I had a question that you can give example where the S process happens,
Uh,
like our process happens in supernova, but where does the S process happens?
it can happen anywhere where it finds neutrons in a steady rate. It can happen on Earth and it can happen on stars also. So I think so. There's a story of Margaret, which who discovered these processes, who proved these processes, this process, by discovering technetium on the sun, because technetium uh, lives. I think so. It's about its radioactive life, and it cannot could not have come from other stars. Anything like any asteroid, meteorite, anything else, it would have formed inside it. And technetium is a heavier element, so this proves provides proof and evidence of the S process in the sun. So this is the story behind the evidence, the process of proving the RNS processes. So did I answer the question?
Um, yes, Aryan,
Okay.
partially you answered.
So conditions for the R process. So the R process require environments with a high neutron density such as supernovas. These processes happen very rapidly compared to beta decay timescales. It involves neutron captures occurring faster than beta decay can occur. The RS process occurs at a slower rate, allowing beta decay to happen between these neutron captures only. There generally takes place in the interiors of aging stars. The process relies on stability environments with moderate neutrons. Okay, so beta decay and element stability. So beta decay converts a neutron into a proton, shifting the elements to a higher atomic number. It plays a crucial role in moving unstable isotopes towards stability. Both processes R and S involve a balance between neutron captures and beta decay. So element abundance and the process. So the R process is responsible for about half of the elements heavier than iron. The S process contributes significantly more to elements like barium and strontium. The distributions of elements in the universe reflect the combined effects of both the processes involved. Isotope signatures of R process. So R process isotopes are typically very neutron rich and stable. They decay into stable isotopes over time. So detections of these isotopes help identify sites of R process nucleosynthesis where R processes happen. So isotope signatures of our S processes. So these are very closer to the line of stability. They show characteristics abundant peaks at atomic mass. These patterns help trace the history of stellar evolution. So some astrophysical sites for the R process. So core collapse supernovas are believed to be primary R process sites. These neutron stars merger have recently been confirmed as significant sources. Both these environments provide the extreme conditions needed for our rapid neutron capture and the astrophysical sites of the S process. So they occur in giant branch stars. It it proceeds during the last stages of this stellar evolution. These stars contribute to the environment of the interstellar medium. Uh, we have done with the presentation, so let's begin with the questions. So, are there any questions by anyone? Section. Do you have any questions? Hello, Section, are you here? Okay, so Mrityunjay bhaiya, are you here? So,
Yes, yes, sir. I'm here. I'm here.
okay, so did you like the presentation?
Yes, yes. It is informative. You have done your research, and I loved it.
So, like, do you have any suggestions on what should be the next topic?
Regarding the next topic, I think you have covered most of the things, and that too, many things more than two times in your talk till now. So, what I would suggest is, uh, from now on, you can read research papers, the latest ones that are being published, like the ones that you have heard. There's a black hole star now discovered. So, you can read about that, and then we can present that in the next talk. It will be nice.
Okay, so what was I thinking is that first I would have covered all the topics from the Big Bang to the four fundamental forces and then try again and try to explain them better. So I also tried to read some research papers. One was the I think so the on the moving force of heat, and the other one was about the black holes of one was of entropy of I also tried Claude Shannon's entropy theory. It was pretty hard, and the Baconstein's also. I also tried to read that, and with a presentation about that. Like I did not include that on the on the presentation because uh, the mathematics was too hard for me. But I also tried to include some basic maths, like some equations in them. So Uh, this is what I tried to add in these presentations. Uh, so I'll try to read more and more research papers. So yeah,
Yes, maybe see, you have 1 week with you. So, instead of doing it once every week, you can read a paper and take 1 week to understand what is happening. See, don't go into deeper theories and equations because you are still starting right now and you need some background for that. So maybe we can just go with latest happenings what in the space community and uh, just read the paper and present it, and it'd be good for you as well as for the audience. You as in because you'll be updated with the latest findings that is going on. And I think many on solar physics we have new scheme CME prediction methods coming up, and then the stars, this black hole star were discovered, and then few on galaxies. So we you can read one paper per week and understand it thoroughly on your as whatever how much you can, and then prepare a PPT and present it. with all the diagrams and graphs of the paper. So it will be better. It will be interesting.
I tried to read another research paper about that, but my exams were going, so I could not do that. So I just tried to explain a little bit of this, and I'll try the next session to read a research paper and make a presentation about it. So
Yes.
yeah. So are there like any personal or any other research papers that you think that I should read about?
Yes, I'll share with you one interesting one, and
Okay,
maybe you can read it, and if you like it, you can present it next week.
okay. So
Yeah,
okay. So I also read that one, the PhD thesis of uh, Cecilia Penny, one of the uh, greatest astronomy PhDs ever given. So uh, I read that, and I did not include the maths in that one, but I tried to include her in my previous presentation. So my previous one was about, like, it was the previous one. So it was about these elements, about the early astronomy, how the prisms and uh, the composition of stars were decoded. So I tried including her in the presentation also. So okay.
great, great.
So like in my previous presentations, I tried. I think so I made three presentations about as entropy till now. Uh, in one of them, I included the clock, Rudolf Claus's one, uh, on the governing heat of on the governing laws of heat. I think so, Bekenstein bound and Hawking radiation. So they were two research papers that I read and tried to make a presentation about. So okay,
Hmm.
okay. So do we have any questions by anyone else? Adriana, Alan, do you have any questions?
I have a lot of questions. Thank you anyway, because I try to understand those items. But let me think first. Thank you. I'm going to do it, I guess.
Uh, can you repeat? I didn't get your voice.
Maybe here is too noisy. I'm not in the correct place. I'm sorry.
Oh,
But I will go to the group, I guess. Thank you.
okay, okay. So, Alan, do you have any questions?
No, no.
Okay. So, I think so. We should end the presentation now. So, thank you everyone for joining us, and we'll meet next Sunday with another topic. Bye.